Patrizio Savi, who is from Italy. He's working in Politecnico di Torino, Italy. Of course, we had worked together. She's an expert in FSS. She was a consultant in Alenia and conducted research on the analysis and design of dielectric radomes after her PhD. Then she worked in a Center for Antennas and Electromagnetics under the National Research Council of Italy for about 10 years. Then she joined the Electronics Department of Politecnico di Torino, which is deemed to be university, as an associate professor, and she currently is a professor. Her area of interest include dielectric radomes, FSS, waveguide discontinuities and microfilters, high altitude platform propagation channels, and a GNSS, that is a global navigation satellite system reflectometry, and for soil moisture retrieval and things like that. And now her current interest is on characterization of micro frequency of novel materials, carbon nanotubes, graphene, etc. So the micro materials, it is currently an important topic, because when we talk about 5G and all, that reconfigurable antennas and devices, so tunable devices, it's a very important component in that. So I request Professor Savi to give her a talk on this topic on tunable devices, micro devices on graphene. So over to you, Dr. Savi.
Thank you very much for your introduction. And this is the title of my presentation. And I am in Torino. Here is a map, and I'm very glad to join you virtually at your conference. And Torino is in a region called Piemonte in North Italy. Perhaps you know Piemonte because in Torino because of the Egyptian Museum and the Fiat car manufacturing, and also Olympic Games, and if you're tasting wine for the special red wine. The symbol of the town is Mola Antonelliana. That is a building that is poor concrete, height 168 meter. And I'm working now in Politecnico. I started my research career as a CNR, then after 10 years as a professor, and then I moved to Politecnico, and Politecnico di Torino started in 1859 and has two buildings for engineering and architecture. The building for engineer is relatively new and is downtown, while for the architecture faculty we have a castle, very nice and very expensive to maintain, that is close to the River Po. And specifically, I am Politecnico as many international students. These are not the last year data, the previous year, but anyway, we have a 16% of international students. And you have the list, and your country is not so high, but anyway, we have 2% of students from India. And I'm specifically working in the electronic and telecommunication department. We have now a new building, and here I am in the red spot just across this bridge. In Polito, there are 11 departments. Each one is devoted to a special research topic. And I work in the electronic and telecommunication departments, but I have many cooperation with DISAT department, that is Applied Science and Technology, and also Mechanical and Aerospace Engineering department. Here is the outline of my presentation. I briefly talk about graphene properties at microwave frequency and of commercial graphene flakes characterization. Then I will move on the tunable devices that we developed with the help of these commercial graphene flakes. We started doing a tunable attenuator, a phase shifter, and antennas with 1, 2, and 3 stubs. Then some conclusion. As you know, graphene is a two-dimensional array of carbon atoms arranged in a honeycomb lattice. And since the discovery in 2004, there has been plenty of theoretical study about graphene and their properties from a mechanical, electrical, thermal point of view and application. In fact, graphene exhibit a high value of conductance, mobility, mechanical strength, so could be used in a big variety of fields. But I'm most interested, obviously, in the microwave frequency range in which I'm working. And at this frequency, graphene behaves as a tunable resistor. What I mean, if you consider a graphene layer deposition that could be drop casted or screen printed, it exhibits general high resistance. When you apply a DC voltage to the graphene deposition, the resistance reduces. So this idea is at the basis of microwave tunable devices based on a standard device modified with an insertion of graphene pad or deposition in order to have these tunability effects. We decided to use commercial graphene. This work was mainly developed in the last 2 years with my colleague Mohammad Yazir. And he was a former student of mine and a master course. Then he did a PhD with Professor Bozzi in Pavia and worked also with Stefano Bellucci. And then he came back to Polito and for 1 year of research assistant. And we started working on these ideas of using commercial graphene in order to have tunable devices. So we started with tunable attenuator, phase shifter, and patch antennas modified with stubs in order to have to change the frequency of operating of the antenna. We decided to use commercial graphene because till now some experiments were done on this topic, but using lab graphene made in the lab. So I had some graphene flakes bought from Nano Innova, is a Spanish company, and we analyzed first these flakes. With the Raman and spectrum and the phasm. Here is in the red curve is the Raman spectrum we obtained for this type of graphene. This analysis was done in cooperation with DZAT and my colleague Massimo Rover. It is a very, very expert on Raman spectroscopy. So he explained me that this graphene could be few layer, 5, even perhaps 10 layer graphene, surely is not monolayer. And looking at the 2D peak, if you have here for a comparison, I have the Raman spectrum of graphite. You see the 2D peak with this bumps. We don't have so much this effect, but the 2D NG peak for us is only 0.5 and it should be more than 1 in a monolayer graphene. Anyway, that was a reasonable graphene type from a commercial point of view, so we used in our analysis this type of graphene. We also did PHESM analysis. Here are two images, different dimensions in nanometer, and if you look at the right images, you can see flakes of graphene, just to be sure that the graphene we were using could be reasonably considered a few layer graphene. And the first components we tried to realize, was quite simple, a tunable attenuator. This is form, we did the design on a Rogers substrate with a thickness 0.78, epsilon is 3.6 and delta 0.004. And we just designed a transmission line, a very simple transmission line with a gap. And in the gap, we inserted by drop casting the graphene. The line width was 1.66 in order to have a characteristic impedance of 50 ohms. By applying a DC bias voltage to the graphene deposition, the graphene resistance drops and also the attenuation. First, we did some simulation in order to understand the dimensions, the optimum dimension of the graphene deposition. If you look at the aspect ratio defined as the length L over the width W, we did some consideration about the influence of the shape of the graphene deposition. So the aspect ratio 1 means a square deposition, and the aspect ratio 0.1 a very very thin rectangular deposition. We choose a typical value of resistance for graphene ranging from 300 to 3000 ohm per square. Modeling graphene as a thin resistive sheet in the ANSYS HFSS simulator, we obtain the transmission coefficient, the S21 dB that you have here. There are many curves because they represent three different aspect ratios, 0.1, 0.3, and 1, and the minimum and maximum values of sheet resistance. We have noticed that, for example, with aspect ratio 1, we have minus 12 dB of S1, and a good range, I mean a good variation. This case is the red plot. So from 300 to 350 of resistance, that is minus 32 dB, we go to almost 12 dB. So the dynamic range of variation with the DC voltage applied is quite good. But if you consider an aspect ratio of 0.1, second case, and is the black curve, dotted and solid, you have minus 3 dB for the transmission coefficient, that is fine, but the range of variation is reduced, is less than 10 dB. So as usually is a trade-off, the shape of the graphene, at least from a simulation analysis, depending on what you want. So we choose an intermediate value of aspect ratio 0.5 that gives minus 6 dB of transmission and a range of variation with the DC voltage applied of 15 dB. Choosing this aspect ratio, then we analyze what is happening, changing the sheet resistance of the graphene again from 350 and 3500. And you can see that you go from minus 22 dB to minus 6. So we expect a similar variation in the experiment applying a DC voltage tuning the position. measurement, we realized the line. It was very simple, just with a standard etching technique. We deposit the graphene flakes with drop casting, just making a mixture of alcohol isopropylic and graphene flakes. And we deposit the graphene flakes on this gap, and then the alcohol is evaporating. And here on the left, you see the measurement. We have two broadband bias T connected to the line, and connected to the radio frequency port of the bias T is connected to the network analyzer. And then we have a DC voltage supply in order to have the different voltage to the graphene part. Here is the first results. You see the value in the table that are plotted in the graph. The voltage applied is from 1 to almost 10 voltage. And from the measuring the current and voltage, then we have the resistance of graphene, and then we can evaluate, given the shape of the pad, of the position of the graphene, we can also measure, calculate the sheet resistance. So we go from a very high value for almost no voltage and current apply is 1000, and then we have a progressive reduction of the resistance up to 9.6 volt. A small break because of the midday, and I'm afraid you're disturbed by the bell. That I don't know if you can hear it or not, and if it's a problem.
It's all right, ma'am. Can wait.
If it's not a problem because of the bell, I go on. And here you have another result, the transmission coefficient as a function of frequency. While we were doing the voltage, DC voltage measurement, we were also using the network analyzer to measure each step the transmission coefficient. So you see what happens from 1 volt, that is corresponding to a very high resistance, up to 10 volt, that is growing. The transmission coefficient is going from minus 18 dB to approximately minus 8 dB. So we were, this is the first attempt of having tunability of graphene flakes deposition was quite good as a result. And we went on and we tried to do a phase shift. So there are many applications of these components in electrical steerable antennas, or for cellular communication, wireless LAN, automotive radar navigation, space system. And the basic principle of this component is to change the path of the signal, and to have a short path and a long path in order to change the phase of the signal. We decided to do this with a configuration based on a transmission line here on the left, and 2 stub line in order to have a symmetric configuration and more effects. The stub line are open circuit at the end, and we model a graphene pad with a resistance here connected to the ground. So the lamped resistor are modeling the graphene, And we have also tapered line in order to go from 50 ohm to 100 ohm line and match all the structure. Again, with this configuration, we started to analyze the configuration, understand the behavior with some simulation based on ADS and HFSS, in order to find the input resistance, a real part and imaginary part, and in order to optimize the geometry. The length of the tapered line here, and also the length of the stub open at the end. And we made some analysis in order to understand how can we have to vary the graphene resistance and the length to have the best results. Here is some data. We tried, here is the length, the column and the length of the tapered line. It was chosen 3 millimeter, 4, 5, 6. Here also the length as a function of wavelength, and the length instead of the line and the stub. And in order to find maximum variation of the imaginary part and relative small variation of the real part for the input impedance, we found that the best solution could be a tapered line of 6 millimeter and a line stub of 0.3. You see that here you have 44 for the variation of the imaginary part. That is the maximum. After this analysis, that was done with ADS. These are model with ADS. Then we did a full wave analysis, considering this time a Rogers substrate of 3035, thickness 1.5 millimeters, and the thickness of the copper of here now see a mistake, 35 micron. Okay, and the line, the width of the line, in order to have an impedance of 50 ohm, is 3.2 millimeter. Here you have a zoom of the one of the stub. You have the tapered line and the pad and the graphene deposited between this pad short circuit and the line. We had to have some distance between the short circuit hole and the pad, so we decided for this small plate in order to be able to drop cast the graphene. And here's some results. We did all the analysis for frequency 4 gigahertz. And concerning the amplitude and phase variation of the S21 parameter, the amplitude variation, you can see that is decreasing for increasing the length of the stub from 0.25 to 0.3. And instead the phase variation is increasing for increasing the line of the stub. So we find an optimum length, at least from a simulation point of view, of 0.3 lambda for the stub. In this way, we can have a minimum amplitude variation and a reasonable phase variation. We finally looked also at the aspect ratio. Also in this case, here the deposition of the graphene as a length and width that can be changed. And so we did an analysis with a different aspect ratio, 0.2, 0.8. And we noticed that reducing the variation, the aspect ratio from 0.2 to 0.8, here is the variation, varies the amplitude and phase, obviously, of the transmission parameter. So we choose the case in which we have a maximum phase variation that this nominal was 73 degree for an aspect ratio of 0.2. Here is the setup, measurement setup. We use this time a portable vector network analyzer, very small here, connected to a laptop, power supply, and bias for radio frequency measurement, and the phase shifter here. Port 1, port 2, here is the prototype, one of the prototype we did of the phase shifter. Not very easy to see, but in this small gap, there are 4 graphene deposition. They're always drop-casted with alcohol isopropyl. And here the results. First, we did again the simulation, looking at the real variation of the resistivity we had with our graphene. And in the second panel, the measurement, S11, the amplitude and the phase. So you can see here in this part, the phase variation that we obtain starting from 0 volt, the orange plot, to 6 volt, that it is the black plot. And here is the variation we had in this work. It was 33 degree. Yes, the theoretical one was much higher, but I think that this first prototype should be further optimized and realized with better technique. We just use the standard etching technique to do all the components. And the figure of merit of the phase shifter, defined as phase shift variation degree on the insertion loss variation. Anyway, in this work is quite good. It's 82. In the previous work of Yazif was only 13. They had a 40 degree of phase shift, a little more, but not such a high figure of merit. So with a design, thanks to simulation and a try and error procedure, we managed to have a reasonable phase shift with a quite high figure of merit. And last components, if I still have time, is the tunable graphene antenna that was designed starting from an idea of Professor Nashdam that was in Torino as a visiting professor for 1 year in 2017, and he was studying a patch antenna with a carbon nanotube film. But carbon nanotube film cannot be tuned with applied DC voltage. But starting with from this idea, we modified the design, optimizing the place in which the graphene deposition should be inserted in this stub. This is a standard patch antenna inset feed, as you can see, but on the radiating edge is inserted in the middle stub, short circuit stub, with a gap, and in the gap the graphene position. And from this design, yes, was done a model in order to understand the position of the graphene. This is the stub, short via, can be simply modeled with a transmission line theory. So a first line of length L1, then the graphene deposition that is modeled as a resistance, and the second line. So starting from the original configuration in which the gap was in the middle of the stub, we defined better performance if the graphene pad is close to the patch antenna. And with a one stub design, the shift in the resonant frequency of the antenna that was around 5 gigahertz was found to be around 200 megahertz frequency shift, at least for simulated results. And this antenna was designed on a Taconics substrate and with a similar results, but we went on and we tried a different configuration with two stubs symmetrically placed along the radiating edge. We had, at least for simulation, a very low reflection coefficient, minus 27 dB, and better shift in frequency. And then we also try a three-stub configuration, but at least for the two-stub configuration, here you can see the prototype that was measured in an echo chamber for the gain and also for the tuning. Here in this table you have the tuning voltage from 0.3 to 10 volt, the current value, and the resistance that in this case was from 700 to 70. And you see what happens to the reflection S11 of the antenna. From 0.3 volt, for example, the blue plot, you go here, the red curve is at 10.5 volt, and so we had a shift in frequency of 350 megahertz by applying this voltage to the graphene pad. And finally, we try a three-stub design. If it's even more complicated to the deposition and so on, and we had even better results, at least in simulation of more than 400 megahertz shift in the frequency due to the DC voltage applied to the graphene part. We also checked the gain of the antenna and we measured the gain, and we found that the gain value, fortunately, in the project was not so much affected by the presence of the stub and of the graphene pad. So with this configuration 1, 2, and 3 stub, we could manage varying the resistance of graphene but applied voltage to have a good tunability of the antenna of at least of 300-400 megahertz. Some conclusion now about all this work. We tried with a commercial graphene to obtain devices that could be tuned with an applied DC voltage. We did a cheap fabrication of tunable components, and also the graphene that was commercially available was not so expensive of a monolayer graphene that could be realized in a lab. And we had good performance on the attenuator and the phase shifter. Currently we are working on the phase shifter. We found a better configuration with a different layout in order to increase the phase variation that was around 33 degrees, and with this new configuration we can get more than that. And we also tried with a patch antenna with a graphene inserted in addition on a stub, and we had an improvement in antenna reflection coefficient, no particular impact on the gain on the antenna, and the possibility of vary the frequency, the resonant frequency of the antenna of up to 400 megahertz. let's conclude my presentation. Thanks a lot for listening, and if you have any questions.
Okay, Dr. Savi. Grazie.
Thanks a lot.
There is one question in the chat box. How does the attenuation obtained vary with temperature?
So going back to the graphene antenna or the attenuator?
Attenuation, yeah. I mean, the property of that graphene, when you apply the voltage, it is varying. So how does the temperature affect on that one?
The temperature, yes. We had to be very careful in doing the experiment in all cases. In fact, at the beginning, we were not able to do the experiment at all because we were burning the graphene deposition. So you managed to do the experiment without burning the graphene by applying for a very short time the current and voltage. So at the beginning, it was the first problem we had to afford. We were not able to do the experiment because after two or three steps, we were, for example, you see the table of value for the attenuator here. Okay, after 2 or 3 steps, we were burning the deposition. Then we understood that was a temperature problem, and we overcome this problem of applying for a very short time the current. Just immediately stop after the acquisition, the current, not leaving everything on and just save data and do other things. And so step by step, we managed to arrive up to 10 volt of voltage applied. And we stop when we burn the graphene, obviously.
There is another one. Can we use graphene for microfrequency without DC bias?
Use graphene as a DC bias?
You can't tune.
Is this a question? I'm not sure to get the question. Volume not in. I think you can do it. We never try. We just started with attenuator and phase shifter design. That was a consequence of the attenuator because from a simple line with a pad of graphene, then we decided to this configuration of a phase shifter and an antenna. So more components can be realized and explored from this point of view of tunability of graphene patch deposition and the components.
I have one or two questions. So you have tried the frequency range, I think it is around 5 or 6 gigahertz. And as you move to higher frequency in that range, that variation was less, that impedance variation, attenuation variation. So what about when you go to higher frequency in X band or like that, will you expect this, or you have to change the voltage more? Because there is a
I think you can go, yes, we work mainly in S band or 5 gigahertz because we realize all the component in our lab, and also because the effect, if you increase the frequency, this effect is reducing. Perhaps I have a slide that can be explained this. Okay, this it seems what is happening going to micro and millimeter waves to terahertz. So the conductivity is changing. Seems reasonably changing, and microwave and millimeter waves, but then it's reduced this variation, and you have no changes. So there is a limit on this. It's better to stay on this frequency range and not to go to terahertz and so on if you want to see this effect.
Actually, it is how do you apply the voltage? It's almost a two-dimensional this thing. You are applying top and bottom or sideways?
Sideways. We were applying the with the sideways for the the graphene pad.
So how does it? Yeah, you have shown with the aspect ratio. I think you have shown that. So that means when you change the aspect ratio, the property also will be changing the way in which you apply the voltage.
Yes. We also did the aspect ratio uneasy because depending on the shape of the pad, obviously also the results is changing.
Okay.
And so from the resistance, we both for the phase shifter, but even plus clear in the for the tunable attenuator. Okay, this analysis we did for the tunable attenuator holds also for the phase shifter and all other components. There is a trade-off on the shape. If it's too thin and the deposition, it is not possible manually to do the position properly. And if it's squared, you have a good range, but of variation, but not a very high value of S1, the transmission is poor. So you always have to first consider the shape of the deposition and simulate and try to find the optimum shape for the application you're looking for.
Okay, thank you. Any more questions from the participants? Please. So if there are no more questions, I thank Professor Savi for this presentation, because I think these are things which we can also try here using this commercial graphene and do some experiments with that one.
I will be very happy if you can cooperate on this.
Yeah, sure.
We'll
try that. So
Thank you, ma'am. And thank you, sir. That was a really good